Hello everyone, welcome to our daily physics problem, day number 30. So today we have a cylinder with mass m1 covered on a horizontal stick AB. Under the cylinder there is a rope connected to the ball with mass m2. Horizontal force F is acting on the ball to the right. The coefficient of friction between the cylinder and the stick is mu. What is the smallest force F in order to keep the cylinder moving? So I want you to pause the video, try your own. After you try it, come back to the video, let me show you how I did it. So welcome back guys. So here we have a tension force again, and we know the tension force have two directions. So it would be better to isolate our system to 2 points, one at point C, one at point D. So by balancing the force, we know there are 3 forces acting on point D and uh, 4 forces acting on point C. The gravitational force, the friction force, and normal force, and the tension force. Tension we said is T. So now by this two systems, we can write two system equations on each system to balance the force and the Newtonian motion, which has acceleration of a. Both the cylinder and the ball accelerating rightward with a. So by balancing the first system and the bottom system, we have F is minus t times cosine theta is equal to m2a. This is F equal to ma. Then t sine theta equal to m2g. Then we divide this as the first system, this is the second system. So on the second system, the horizontal direction, or in the vertical direction, we have m1g plus t times sine theta will be equal to the normal force. Then the friction force is normal force times mu. Then what is uh, the on the horizontal direction? We have m1a is equal to t times cosine theta minus f. That's our F equal to ma identity, Newton's second law. Then based on these two system equations, we can solve for F. What is the minimum of F? We know from the first equation, F minus a number have to be acceleration times mass. So if we want to say the acceleration is very, very small, even just a little small acceleration, then F had to be bigger than t cosine theta in order to have some certain acceleration over m. Then we can solve for t equal to m2g divided by sine theta. Then F will be bigger or equal to m2g times cotangent theta. But that isn't the answer, the final answer. It will be useful though, but it's not the final answer because it's only a circumstance to move the ball, but we need to move both the ball and the cylinder. So F could be a little bit more smaller, could still be a little bit more smaller. So by looking at the second equation, we can solve for also if A is very, very small, then t times cosine theta is bigger than or equal to f. Then t will be bigger and equal to f divided by cosine theta. Then we know t is equal to m2g divided by sine theta. This is still true. So we plug them back in. And we know f equal to mu times n. And we know the expression for n, we just plug it back in. Then we can plug the f equation back into our inequality. We have mg times cotangent theta. We multiply both sides by cosine theta is equal to mu times m1g plus t times t will be equal to m2g divided by sine theta again times sine theta. Sine theta cancelled out. Then remember we have m2g times cotangent theta. What is that? That is our minimum force in order to move the ball. Remember? So we can replace it in because from the left hand system equation, we know F is bigger than equal to mg times cotangent theta. And mg cotangent theta have to be bigger than mu times m1g plus m2g. So that we know F have to be equal to or bigger to mu times m1g plus m2g. And we factor out the g, we have mu g times m1 plus m2. And that's our final solution. Thank you for today.